We now discuss conductor dielectric boundary conditions, and we are going to follow the similar procedure that we have followed for our dielectric to dielectric boundary conditions. And from figure 512, we see a conductor. One of the medium is a conductor, and the other one is a dielectric. We want to develop for both the E. When we use this diagram for developing the D or the electric flux density conditions, and this we normally use it to develop the electric field conditions across the boundary. And first of all, we assume that the conductor is perfect, and therefore we have sigma approaches infinity, and therefore no charge can accumulate in the surface. And we say that this may not be practical because such conductors having infinite conductivity do not appear in real life, but we say that we may assume that we can treat copper and silver as perfect conductors. So in that case, what we know is that no electric field can accumulate in a conductor. That is something we saw earlier. So the only terms we are going to be left with is E. If we call this one our 1, this one our 2, and this one our 2 medium 2, then we can know that when we are talking about E1 of t across the conductor being equals to E2 of t being equal, since we have said in the conductor E can only be 0 because it's a conductor, then this becomes 0, and therefore we say that or E1 of t is equal to 0. And similarly, we said that from just borrowing heavily from what we have done earlier, we have said that the electric flux density across the two medium are continuous, but we know that since we have seen that E2 is equals to 0, and therefore we can say that D2 of L is equals to epsilon 2 E2 of N, and since this is 0, this goes to 0 as well, and therefore this equation also goes to 0, except for one condition. If there was a service charge accumulating on the service, then this will be 0. So let's just now go through the notes and see how that comes about. So we are saying that we are following the same idea that we have done for the dielectric to dielectric interface, except that we incorporate the fact that E is 0 inside the conductor. This is something we have already met in the past. And therefore, if we follow the same idea we followed, we are going to observe that this term goes to 0 and this term cancels out. We are only left with these two. But these two, we know one of them goes to 0, and therefore we end up with E of t being equals to 0. That is the first condition, the boundary condition that we state for a dielectric conductor boundary. The other one is the one that we considered for a cylindrical pillbox, and we said that the charge incoming or the rate of change of charges across the boundary is equals to the flux coming and the flux going out. But we know that flux cannot be going out cannot be coming in. The one coming in is coming in. This is the one that is going out. It is the charge that is accumulated in the on the surface of the boundary. So if we know that this is a conductor, this is going to be 0, and therefore equation 568 becomes change in Q is equals to dn dot ds. And of course, we have said this happens because this is 0 in the conductor. And therefore, our condition becomes our new boundary condition if there is some charge that accumulates on the surface of the conductor that is described as surface charge density rho s, and then our D normal will be given by the surface charge density rho s. And this becomes our new boundary condition for that interface between the conductor and the dielectric. Thus, under static conditions, the following conclusions can be made about a perfect conductor: that there is no charge that accumulates, or there is no electric field that may be visible, may be measured within a conductor, and therefore we make that conclusion that there is no charge can be inside the conductor. In number 2, we also said that there is no potential difference between 2 points in a conductor because we say that a conductor is an equipotential body. And lastly, an electric field must be external. And from this equation, we say that electric field must be external to the conductor and must be normal to the surface. So anytime we have some electric field in the conductor, it cannot be generated from within. We cannot say that this field is coming from within or due to polarization, like we said with dielectrics. It can only come from outside, and therefore it is going to be given by, we are going to have the tangential component being equal to 0 and the normal component being given by the surface charge density. It must always be normal to the surface. That is why we are saying that the only component that is parallel to our surface of the conductor is going to result to 0, because this is going to cancel with this, and therefore we end up with 0. But the normal one is going to give us some flux that is passing through the medium or the conductor, and therefore that flux is going to be equivalent to the surface charge density on the surface. So an important application of this, or the fact that no electric field can be found inside a conductor, is in a concept that we normally call electrostatic shielding, whereby we say that we are going to consider figure 5.1.13, and this figure says that if we put a certain conductor inside another conductor that is grounded, like we can see in figure A here, or figure 1.3, then this is a conductor that is grounded. Then we normally say that conductor B is shielded from C, that the fields associated with C are completely independent from the fields that are resulting from B, and therefore these two conductors are said to be completely shielded from each other. That is what is called electrostatic shielding. So we're saying that from figure 1.3 that B is said to be electrically screened by A from other electric circuits, such as conductor C outside A. And similarly, conductor C is also said to be screened by A from B. So both of them are shielded from each other, and the electrical conditions inside this shield and outside the shield are completely independent of each other. And if you apply the concept that is we have developed, we can also see that a conductor and a free space will give us similar conditions like that of a conductor, except that the dielectric will have the free space does not have ER, and therefore if there is some surface charge on the conductor, that will result in the normal flux density normal to the conductor being equivalent to the surface charge density accumulating on the surface of the conductor. So in conclusion, we say that the conductor free space boundary conditions that we have that are illustrated in figure 1.4 below comprise of a special case of conductor dielectric conditions, because we are considering our free space to be a special case of a dielectric that has ER to be equals to 1. The boundary conditions at the interface between a conductor and free space can be obtained from equation 571. Just 571 is the one that we have just stated here for a conductor dielectric condition. And by replacing ER by 1, the electric field E must be external. We conclude that the electric field E must be external to the conductor and must be normal to the surface. That is what we are saying here. That thus the boundary conditions that we state for conductor free space boundary conditions are these two: that the tangential components of electric flux density along the boundary is 0, and the normal component of electric flux density across the conductor free space interface can only be equivalent to the surface charge density on the surface of the conductor. It should be noted again that section 572 implies that the E field must approach the conducting surface normally. So we say that electric field must approach the normal. It will be only get the normal component in any tangential components of the E field goes to 0.